Welcome back to Cougar Chem Tutoring. I'm Austin, and I'll be running through part 2 of problem set 9, periodic table and trends. All right, number 5. The compound lithium bromide consists of lithium cations and bromine anions. The lithium and bromine ions are not the same size as they are in the elemental state. Okay, explain how their relative sizes change in relationship to their size in the elemental state. Okay, well, lithium, let's say it was this big, or no, let's go this big, okay? If it becomes positive, we're now turning it into lithium positive. Okay, we lose an electron. Okay, so we lose electron. Okay, so I'll have it come out of here right there. Okay, so what should happen now? If I think about the nucleus of lithium, and I've got these valence electrons out here. Okay, this pull on one of these electrons is now not distributed between two electrons, it's distributed only to one. And so now it's pulling it really, really tight, right? Now it's going to pull in that electron super tight. And so now it's going to turn smaller. It's going to turn smaller. So in terms of becoming a cations are always smaller than their elemental forms, okay? Smaller than their elemental forms, okay? Not than any other thing. It'll be relative to whatever the element that you're working in. Than elemental state. All right. Okay. Now, opposite happens for anions. Okay. So negatively charged things. So let's say bromine is this big. Okay. Now we gain an electron. So plus an electron. So gain. And now what would we expect bromine minus to look like? Well, we've now let's say here's the nucleus of bromine right here. And let's say we have a ton of layers out here. It's going to be hard to draw all of those, okay? But on these outermost electrons out here, okay, it's going to be, we're now adding another electron into it. So this electron, let's say the electron right here, we're now adding this to the mix. So now the pull that the electrons, or that the nucleus was feeling with each one of the electrons in the valence shell for bromine is now distributed amongst more electrons, and so each pull is now weaker on each individual electron, so it actually loosens up a little bit, and so it becomes slightly bigger. So I'm going to just try to draw this a little bigger, okay, just like that. So anions, negatively charged things, right, negative, are always bigger and relative to their elemental state, okay, relative to the elemental state. All right. Okay, number 6, part B of number 5. Okay, in the depiction of the crystal to the right, of the salt to the right, which ions are the purple ions and which are the green? Well, we would expect the smaller ones to be the cation, right, and the green ones to be the anion. So we'll say probably purple is going to be lithium, and that green is going to be bromine. Okay? All right, number 6, which of the following atoms has the smallest first ionization energy? Okay, in order to do this, we'd have to go to the periodic table up here and determine where each of these are, and based off the trends, figure out which one has the smallest one. Okay, so we know that it increases up and to the right. Okay, so up and to the right. So I'm going to circle the ones that we're dealing with. We're dealing with oxygen, we're dealing with bromine, with barium, with tin, and with francium. Okay, so now what does the arrow here mean? This is increasing ionization energy, right? Increasing ionization energy. So that means the ones that are in the farthest down and to the left are going to be the ones with the smallest first ionization energy. And as you can tell, it's probably going to be francium, right? And actually, francium is incredibly reactive because it can lose that electron so easily. In fact, it's so reactive that there's hardly any of natural francium on Earth. There's only about, I think, 15 grams. All right, number 7. The first ionization energies of beryllium and lithium are about 900 kilojoules per mole and 520 kilojoules per mole, respectively. Okay, yet the electron removed from both of these originated in a 2s orbital. Okay, explain in 1 to 3 sentences the large ionization energy differences observed between these elements. Okay, so if I have an orbital diagram here, this would be lithium right here, right? But this would be beryllium. Okay, and we've got 2 right there. So why does it take more energy to just take one of those electrons than to take the one from lithium? And you could technically say because that's how the trend goes in the periodic table. But the problem is that they're expecting you to know why that trend exists. And it exists because of effective nuclear charge. Okay, here comes that term again, effective nuclear charge. And you'll see this written as Z effective, like that, okay? It's that effective nuclear charge is larger in beryllium, right? Because beryllium has more protons. If we look in the periodic table, lithium has 3 protons while beryllium has 4 protons. And so it's got a greater grip on its valence electrons, right? So if let's say I draw the 3 protons here in the nucleus for lithium, and I've got the 1s, and then now the 2s, so I got the 2 electrons here, and then I've got the 1 electron for lithium, and then I got almost the same setup, except I have 1 more proton in the nucleus. I get the 1s and then the 2s. Now, can you see, now that I have this stronger pull on the most outer valence electrons, okay, it's going to be harder because now I've got more positive pulling in the two valence electrons. And so it's going to be harder to take it off beryllium because its effective nuclear charge is larger on beryllium. Okay, and so it's gonna take more energy to break this attraction between the nucleus and that outer valence electron in order to pop it off. Okay, so however you want to explain that in 1 to 3 sentences is up to you, but that's kind of how you want to answer your question, always in terms of effective nuclear charge. Okay. All right, so part B says another particularly interesting exception to the trend is in first ionization energy is found by comparing phosphorus to sulfur. The first ionization energy is higher for phosphorus than for sulfur, even though sulfur has 1 more proton in its nucleus. Explain this phenomenon. Okay, so this is interesting, right? Because normally we've been, defending ourselves using effective nuclear charge, but in this case, in theory, right, the effective nuclear charge should have been stronger for sulfur, making the first ionization energy higher than phosphorus. So if you look in the periodic table, phosphorus comes right before sulfur, so it should have a lower first ionization energy. But let's see why it might have a higher. So to do this, it would be helpful to draw orbital diagrams. So P, phosphorus, is in the 3p, and it's going to have its valence shells in the 3s in the 3 shell. Okay, so we've got the 3s and the 3p orbitals. I'm going to do the same thing for sulfur over here. Okay, so I got my 3p orbitals and my 3s orbital here. Okay, all right, so now I'm going to fill this in. Phosphorus has, let's see, 1, 2, 3, 4, 5 valence electrons, and then sulfur just has 1 more than that. So I'm going to fill in 1, 2, 3, 4, 5. Okay, and then 1, 2, 3, 4, 5, 6. Okay, so why would taking this electron right there, the one that's right here, cost more energy than taking, say, this one over here on phosphorus? Well, if you remember from our exceptions to the D subshell, remember when a D subshell that has 5 orbitals, remember each D subshell has 5 orbitals. Let's say this is the 3, okay? If we have a half-filled shell or a fully filled D subshell, that is more stable than a regular 4s orbital. And so we by default, when we were ionizing things, we'd actually take it from the 4s because this thing is very stable. Okay, having it half filled is very stable. Having any orbital designation is half filled or fully filled is always more stable. So in that same spirit, if you look at this, it's going to take less energy to get this because not only once you take this from sulfur will it become half filled, but if you were to take this from phosphorus, this would no longer be half filled. Okay, so we've got the two going for us, that if we were to take it away from phosphorus, it now loses its stability, but as we take it away from sulfur, it actually gains its ability. So at this point, when you reach that part this is group 15 in the periodic table, you're going to notice this trend. It actually breaks the trend that we normally see in the periodic table, where we have the increasing ionization going this way and this way on the periodic table, because of this phenomenon where we have a half-filled P subshell, and then going on to the next group where we would be removing that to gain the half-filled subshell. Okay? All right. Number 8. An electron can be removed from lithium or cesium by electromagnetic radiation, the photoelectric effect. Which element, lithium or cesium, would require the longest wavelength to remove the electron? Okay, longest wavelength, that's just keyword. If you think about the longest wavelength, okay, that means it's got the lowest energy. The lowest energy. So longest wavelength, I'm going to put longest lambda is equal to lowest energy, okay? Because if it was talking about shortest wavelength, right? Shorter wavelengths have higher energy. If it had asked for shorter wavelength, then we would have said, okay, it's now looking for the highest energy. Which one would require the highest energy to remove the electron? But they're asking for longest wavelength, which is lowest energy. So which one's going to cost the least to remove the electron? So remember that ionization energy if I'm going to take this periodic table and expand a little bit, that the ionization energy increases this way and increases this way. If I look at where lithium and cesium are, they're right there. Okay, so that means cesium, because it's lower, it's going to have a lower ionization energy, which means it requires the longest wavelength. So cesium. Okay, cesium, because it requires the lowest amount of energy due to this trend on ionization energies. Okay. Now on to number 9 here. I'm going to keep this periodic table up here. It says, based on the positions in the periodic table, predict which atom of the following pairs have the most electron affinity. Okay, most negative electron affinity, which is just saying the most electron affinity, because the electron affinity increases in negatives towards the right and up. Right, so we said it increases to the right and up, but it increases in orders of in magnitudes of negative. So this side is more negative. All right, which just means it's releasing more energy as you add an electron. All right, so 9 says, so the options for 9 say A is fluorine or neon. So we got fluorine or neon. Okay, well, following the trend, neon is to the right of fluorine, right? So in theory, it should have a higher or a more negative electron affinity. But here's the problem, is neon is a noble gas, right? Neon is a noble gas, and it's already got the perfect octet around it. It doesn't want to open up a new subshell and add an electron. And so this is actually counterintuitive in that this is one of the exceptions to the trend in electron affinity, is that the noble gases will have a very positive, meaning they don't like to have electrons added to them. They don't have very positive at all. And so fluorine's actually the most has the most electron affinity. So we're going to circle fluorine on that one. Okay. All right. So rubidium or palladium. So rubidium's right here and palladium's right here. Well, strictly based off the trend of electron affinity, we're going to expect rubidium to have less electron affinity. So we're going to expect palladium, just based off the trend that it's going this way, to want to add one more. Okay, so we're going to say palladium. That's the most negative electron affinity, meaning it has the higher electron affinity. All right, C, oxygen or silicon. Okay, so we got oxygen right here and silicon. Well, oxygen is not only up, but it's right of silicon, right? And so it's going to have more electron affinity than silicon. So I'm going to put oxygen there. And then the last one I got germanium and selenium. Well, and given that they're in the same period, selenium is to the right, we can just assume that selenium is going to be more negative, just because it's simply to the right. All right. Okay, last one, number 10. Photogray lenses for eyeglasses darken in bright sunshine because the lenses contain tiny transparent silver chloride crystals. Exposure to light removes electrons from chlorine ions, forming a chlorine atom in an excited state, indicated by the asterisk below. Okay, the electrons are transferred from the silver ions, forming silver metal, so we get this. Okay, so the silver is metal is reflective, producing the photogray color. How might the substitution of silver fluoride for silver chloride affect the light sensitivity of photogray lenses? In answering this question, you want to consider whether there's more or less energy needed to remove the electron from an F ion or from a chlorine ion. Okay, so let's condense this down. If we hit the chlorine ions with light, okay, it creates our silver metal, right? And the silver metal is the reflective that we're able to produce. So we have a certain energy per photon that's required to knock off that electron. That electron then reacts with the silver, becomes reflective, and then helps the sunglasses keep away the light that they need to, the photogray lenses. Okay, so if we replace that with fluorine, if we said this is fluorine minus, how would that change? Does it take more or less energy to knock off the electron from the fluorine to create an excited fluorine ion or atom? And if we look at the trends, remember the trends follow up and to the right for higher ionization energy, because that's what this is, right? We've knocked off an electron. This is ionization energy. And this is an example of ionization. And the energy that we put in was just from that light. So does it cost more or less? And the answer is it costs more, right? Because fluorine is above chlorine on the periodic table. So because it costs more, it's going to be less sensitive to light. So we'll say less sensitive to light, because it's going to take more energy to take that electron away from the fluorine, okay? Less sensitive to light. meaning that when we want our photo gray lenses for eyeglasses to darken more, they're not going to darken as much because they need more light or more energy to hit them in order to knock off these electrons, react with the silver plus ion to create silver. Okay? All right, well, I hope that was helpful. We'll see you in problem set 10.